Everybody, this is Mr. Perry, and I wanted to do a quick video here, especially for students who were absent when we started talking about number conversion systems, base 10 to base 2 number conversions. And if you were gone for the introduction to the ASCII chart, this is essentially all of the information that was covered yesterday. So one of the first things we did as a class is we looked at our base 10 number system. And you'll notice that this is set up just like the flippy-do, all right? When you learned to count in binary, we had 2 to the 0 power, 2 to the first power, 2 to the second power, and then it said, 1, 2, 4, 8, and so on. So what we're doing now is basically looking at, our normal number system, which is a base 10 number system, and we're looking at, again, how we would modify that flippy-do to represent our method of counting. So we would start in this first column over here with a number 0, and then we would go up to 1, and of course we can count to 2, to 3, to 4, and to 5. And this is going to continue all the way up to number 9. And then we're kind of stuck because we went from 0 to 9, and we can't get more than one digit in any specific column. So what we do next, of course, is we add a 1 over to here, we shift this back down to 0, and then it continues, so on and so forth. Just like the odometer in a car, counting the miles, right? You've got your ones column, your tens column, you've got your hundreds column. So if we add 1 here and then 2 zeros here, this is basically how our familiar number system would work if we were to represent it on a flippy-do. So this would be the number 19,507,182. And again, the 1 here just indicates we have one value of 10 million. 9 here means we have 9 values of 1 million, and so on and so forth. So this was just a quick review of how number systems work and how our base 10 system is designed. And one of the big takeaways that we had in the discussion was that in each specific column, you can go from 0 all the way up to 9, which of course is 1 less than 10. And then if you have to add an additional value, you have to shift over to the next column. Now we're going to go back and look at the flippy-do. And again, just remind ourselves of how this flippy-do works and see the similarity. So if we were counting in binary or a base 2 system, you would start with 0. Then you would go up to 1, and then if we added a 1 over here, we now have one value of 2 plus one value of 1, which is 3. So this is the number 3. This, of course, would be the number 5, because you would have a value of 4 plus a value of 1, and so on and so forth. If we filled the whole thing up with a bunch of 1s and 0s, you would have 128 plus 32, which is 160, plus another 16, which is 176, 180, and 181. So this would be the binary version of the number 181. And again, this is called a base 2 number system. So moving forward, later on in the class, later on in the week, we're going to talk about number conversion. And at this point in the class, you want to ask yourself, how comfortable are you converting from base 10, which is decimal, to base 2, which is binary? Similarly, how comfortable are you going in the reverse? How comfortable are you going from base 2 to base 10 or binary to decimal? At the class schedule, at the class website, I did link to some binary number games. So this can help you practice that process. And they are separated by easy, medium, and challenging. So you can kind of give yourself an appropriate level of review. Now looking forward in the class, I want you to think about how would that flippy-do change if you wanted to work in a base 5 number system. Which of those numbers in the flippy-do would you have to change, and how would they change? And then again, what numbers would you have to work with in each column? What numbers would you be able to count with in a base 5 system? Eventually, we're going to talk about a base 8 number system, and then really importantly, we're going to talk about a base 16 system called hexadecimal. So this again is just getting you thinking a little bit further down the road what we're going to be doing in this class. Now today, our specific area of focus is how we went about digitizing letters and characters. Now that you know the difference between the analog or the real world versus the digital world, where everything has a numerical value and you know, we're basically turning real things like letters and words into numbers, values that can be stored on a computer. And we paused momentarily and I asked you guys to look up what was the first message ever sent from one computer to another. So if you want to pause the video and look that up, you can. If not, you know, we're going to move forward. Because now that we're talking about digitizing letters and characters, we're going to talk about email, and we're going to talk about, you know, sending texts from one phone to another. So somebody created this thing called the ASCII chart, which is, again, how we're going to take letters. So here's letter A, capital letter A, as well as characters. So here's the exclamation point and quotation marks. How do we turn these into numbers that we can feed into a machine? And it turns out when you're looking at what's called the standard ASCII character chart, which uses 7 bits, you read the row first and then the column. So if we look at A, for instance, our bit string would be 0100 0001. And if you plugged that into the flippy-do, you would see that this is 64 plus 1, which is number 65. So B is 66, C is 67, and so on and so forth. If you wanted to look at letter W, you would say, okay, well the bit string is 0101 0111. That's how you would read the bit string for W. So again, you read from this way and then top to bottom. And that's basically how they went about taking a keyboard and digitizing it, all right? Now what's interesting is this 6th bit right here, if you look close, actually represents the shift key. Because you can see here where that's all zeros, you have capital letters, but then down here on these bottom rows where that bit is actually engaged and you have the number 1, you have all of the lowercase. So there is a system put in place, but this is a 7-bit system, because you'll notice this 8th bit representing number 128 doesn't get used. So it's, again, starting with this 7th and then using the final 4 here. Now there is an extended ASCII character set, which does include the 8th bit. So you can see here's the bottom half of that ASCII chart. And here's where they encoded a lot of the specialized characters used in certain languages, like vowels with the tilde or the accent mark, and then you can see there's some Greek symbols that are in here. So there is an extended character set or an extended ASCII chart that uses the 8th bit. But to be honest, all of this is way more technical than you need to know for my class. The only thing you ever really have to do on my class is to understand how to look at this chart, which gives you the decimal value and tells you what it translates to for the letter of the alphabet. So again, letter A is 65. You would then just use your flippy-do to look at, well, how do I represent 65 using zeros and ones? And so for today, what I asked you to do, and I'll take you to the handout in just a second, is I asked you to come up with a question and to write it down, and then use this chart to figure out, well, what are the numerical values for each letter of my question, and then represent that whole question using nothing but ones and zeros. All right, so let's get a look at the handout from today and what it is that you have to do. So this will be posted at Classroom, but this again is the chart that you were given, and this is what the handout looked like. So you wrote down your name. It says come up with a class-appropriate trivia question that's based on general knowledge. So you can say, what are the colors of the rainbow, or how many planets are in the solar system, whatever. And then once you come up with the question, again, look up the numerical values here. So if I did what color is this guy, for instance, the first word I would have to do would be the word what. So W is 87, H is 72, A is 65, and T is 84. So you would then take all of those decimal values and look up what are those in binary. And your goal is to, right here, represent that question using nothing but zeros and ones. So if you were gone today, this will get you X for watching.